So, hello, my colleagues, and I do hope everyone is well. So, I want to pick up on chapter 4, where we left off. And what I'd like to do is go play this example for you. I hope it plays. It looks, I don't know why it's so blurry, but I'm going to try playing this and then we'll move on.
Okay, here we have a savings plan problem. You often have a plan of how much you're going to save every month, every year, and you wonder how much will you have at the end. And in this case, we're going to put $1,000 today and then $1,000 at the end of each of the next 2 years. And we can earn 10% interest, and we want to know how much will we have at the end of 3 years. So what we're going to do is a little different than what we did in the text. In the text, we showed, well, naturally, you could figure out what the future value is of each of the cash flows individually and then add them up. And remember, that reminds us of one important point, which is that once you have all of the cash flows lined up at the same point in time, then you're allowed to add them together. You can't add $1,000 in now to $1,000 in year one to $1,000 in year two. Those are different cash flows because they're different points in time. Once we compute all the future values of year three, then we can add them up and we'll know how much we have. So that's what we did in the text. What we want to show in this example is that there are other ways to answer the same problem as long as you apply the rules consistently. So if we go back to our cash flows, $1,000 now, $1,000 in a year, $1,000 in 2 years. Again, we can't add these together because they occur at different points in time. Right? So that's our first rule of valuing cash flows. What we could do is we can get the present value of the cash flow in 1 year. We would get that by taking $1,000 and discounting it back 1 year at 10%, and that's going to give us $909.09. And you could do the same with the cash flow in 2 years. Now we have to discount it back 2 years, so it's $1,000 over 1.10, because that's 1 plus the interest rate of 10%, squared because of the 2 years. And that's going to give us $826.45. And our answer passes the smell test because we know the present value of $1,000 received in 2 years has to be less than the present value of $1,000 received in 1 year. And it is. 826 is less than 909. Now that we have all of the cash flows lined up at the same point in time, now we can actually add them together because they're all present values. And if we add them all together, we get that the sum is $2,735.54. And so the present value of these three cash flows is $2,735.54. And it's worth noting that what that means is that we could have just put in that amount today. If we just put $2,735.54 in the bank today and nothing at any other point in time, we would end up with the same amount in 3 years as we would if we put $1,000 in today, $1,000 in 1 year, and $1,000 in 2 years, because that's what a present value tells you. It is the equivalent of these three cash flows. So we're not done because we don't want to know what our savings plan is worth today. We want to know how much will we have at the end in year three. So what we have to do is take this present value and turn it into a future value. Well, we know how to do that because you take a present value and turn it into a future value by just applying the rule that the future value is the present value compounded. So we know the present value, $2,735.54. We know the interest rate is 10%, and we've got 3 years of compounding to go from year 0 to year 3. And we get our answer of $3,641, which is the same result as we found in the text where we took each cash flow and moved it to its future value and then added them up. And that's not surprising because either way, we're applying the rules of valuing cash flows consistently. So $1,000 a year now and for the next 2 years gets you $3,600 in 3 years, or just depositing $2,735.54 today and doing nothing else will also grow to $3,641 in 3 years.
Okay, so I hope everyone was clear on that. I hope everyone was clear on that. So let's now go to the present value of a stream of cash flows. We're going to value a stream of cash flows. Okay. And here's the cash flow. Here's the timelines. And here you are bringing it back to the present. Okay. So here you are bringing it back to the present. And you can clearly see here the present value of the stream of cash flows. You do it for each year. You could do it singly, again, or you can use Microsoft Excel. And you could take, if you want to take that amount here, this is the present to the future, in 4 years you get that, okay? So let's go through these again. Let me make sure I'm not repeating anything here. Hold on. No, I'm not. All right. So let's go through these again. Let's look at these examples here.
Okay, so you want to buy a new car. Luckily, you have a rich uncle who's willing to lend you the money. You'll be able to pay him $5,000 a year from now, and then $8,000 per year, 3 years after. The question is, how expensive a car can you afford to buy? If Uncle Henry doesn't lend you the money, then his other option is to put it into a savings account at 6% a year. That interest rate, how much can you afford to pay? Well, the answer is the present value of the cash flows that you're going to pay Uncle Henry. So to put the cash flows we would pay Uncle Henry on a timeline. To find out how much money we can spend on the car, we simply take the present value of these cash flows. Then we take the present value of the first cash flow, discounted for 1 year at 6%. The second cash flow, discounted 2 years at 6%. The third cash flow, discounted 3 years at 6%. And the fourth cash flow, discounted 4 years at 6%. Adding that up, we get a total of $24,890.
All right, now let's look at part 2 here, okay?
Is your uncle really indifferent between lending you the money or putting the money in the bank? Well, he's going to lend you $24,890. If instead of lending it to you, he put it in the bank at 6%, after 4 years, he would have the future value of that amount, which amounts to $31,420. Now let's see what would happen if your uncle took each of your payments and put it into the bank when they arrived. The first payment of $5,000 arrives at the end of the first year, so there would be 3 years left in the bank. The second payment of $8,000 arrives after 2 years, so that would be in the bank 2 years. The third payment for 1 year, and the fourth payment wouldn't be in the bank at any time. Adding that up, the future value of that payment is exactly the same as the future value we had before, $31,423.
All right, so that's a good example. And those 2 examples were great. And so here's the equation for the future value of a cash flow given a present value. Okay, so there's the present value. So this equation, again, is in Excel, right? Microsoft Excel. So you should know that. All right. Okay, so let's talk about the net present value now. and I think I've talked to you already about net present value is built into Microsoft Excel. Let me highlight this, okay? But it only has this piece right here. It does not do the subtraction of your initial investment, okay? So basically, you can actually, you have to bring all the benefits back and, have it as subtract of the present value of the costs, okay? So here is an example of net present value, and you can see this is negative because this is your initial investment, right? I hope everyone's clear about that. And here's your cash flows. So the net present value is positive, so this is a worthy investment. So you want to do this investment. So you can see, so it says here, look, we should make the investment, okay? As long as that's positive, you want to make the investment, right? All right, so anyway. All right, so that's an important consideration. All right, now here it is in Excel. It's best to use it in Excel. And here are the cash flows, and here's the initial value, right? Here's the initial value. All right, so the net present value is basically at 10%. You notice this is negative, right? So here's how you basically, here they are all set up, but here's how you do the actual math, all right? So you got to get the present value of your cash flows here, okay? You get your present value of your cash flows, and then just subtract off this value right here. Anyway, so there's a comment here about Excel. Excel has a built-in net present value function. This function has the format NPV rate, where rate is the interest rate per period, and so are the cash flows, right? Look here, so right here. Unfortunately, however, the NPV function computes the present value of the cash flows, assuming the first cash flow occurs at date 1. Therefore, if a project's first cash flow occurs at date 0, we must, and here it is, we must add it separately, okay? We have to add it separately. So here it is. So it's an important thing you have to know about. All right, so here it is being added separately, okay? B3, you see that? So I just want to make sure everyone's clear about that. So please go over this example. It's very important so you don't get screwed up. All right, so perpetuities, perpetuities from the word perpetual, goes on forever. So it's basically a stream of equal cash flows at regular intervals, and here's the magic words. They last forever, okay? One example is it's called a console, which is a bond that pays you forever, okay? So here's the timeline for a perpetuity, and you can see it's going on forever here. All right, I'm going to have to cut this off. I'm almost up to 14 minutes. I think it doesn't want me to go past 15 minutes, and then I'll make a part 3.